The title of the presentation is Time Memory Trade-off Analysis of Graphs in Password Hashing Constructions. This is the overview of the presentation. Just clicking introduction. I already have introduced that what is password hashing. Again, I am just giving a brief that we enter the password and the password hashing algorithm turns it into some random looking string. So this is called password hashing. The major requirements again in terms of the time memory trade-off, we have many requirements for password hashing algorithms, and here we are introducing that oneness, memory hardness, and constant time operations. Actually, memory hardness is very much required for password hashing algorithms because if less, we need that if less memory is available than the actual requirement, and then the operation should take significantly longer time. Actually, time memory trade-off defense is required to restrict the adversary to compute the password hash. Now the motivation for this work is that most of the password hashing algorithms claim that memory hardness, but we don't know how to verify this because we don't have any easy way to test memory hardness. Here in this paper we have provided how to analyze the algorithms which can be represented through a graph, specifically with directed acyclic graph. And we have provided a very simple algorithm to traverse this, the graph, means the algorithm that can be represented with the help of a graph, and we are providing one simple technique to analyze the time memory trade-off for the algorithms. And basically we have, in the paper we have compared Catena and Rig. Rig is our construction for password hashing. The term time memory trade-off is defined by Hellman as the product of time and memory, where time is the number of operations required for the algorithm and the memory M is the required memory. This is very much important because we know in terms of cost, CPU cycles is much less than the RAM space. So every time adversary tries to use to get the output with implementing with less number of less memory as in place of the actual memory required for the algorithm. Our solution needs some basic, to explain the algorithm we need to introduce some definitions. This is directed acyclic graph. I think I don't need to explain it much. The graph which doesn't include any cycles is called directed acyclic graph. And this is bit reversal permutation. This is a permutation defined on the elements where the number of on the array where the number of elements are in power of 2. We assign we index the element from 0 to if suppose it's 2 power k, then 0 to m is 2 power k, then it's the index should be 0 to m minus 1. Then the permutation will be the bit reversed of the indices. So this is the graph showing the bit reversal permutation. These are some simple graphs, and the name of the graph depends on the it is basically derived from the dependency between the nodes. See, this is sequential. This is sequential because they are all the nodes are dependent sequentially, and this is vertical graph. Like this bit reverse graph is this one. This is bit reverse graph, and because the relation between the nodes satisfy the bit reversal permutation, and this is butterfly graph. Next we defined a straight graph. Straight graph is the overlapping of sequential and vertical graph. You can, if you remember, see this is sequential, this is vertical, and now this straight graph is having both the relations sequential as well as this vertical. So we call it straight graph. Now this is bit reversal graph. It is the overlapping of sequential and bit reverse graph. And this is bit reversal straight graph. It has three dependencies: sequential, vertical, and bit reversed. And our construction tree follows this graph. This is butterfly graph. It is defined in catenate DTG can be explained with this graph. It is the combination of sequential, vertical, and butterfly graph that I have already shown. Our proposed technique is a simple algorithm. It shows how to traverse such graphs. Here, these are the steps. I think it will not be that easy to follow. So I am just switching to the example to make it clear. This is one simple example showing 4, 2, 4, 2 in the sense that number of nodes are 4 and 2 is the levels. So this is 4 to bit reversal graph. In that, suppose we have to calculate this. Actually, 3, 2. This is the final password hash. If you imagine that this is the whole design which is showing your password hashing algorithm. It has started from this node and it ends with this one, this last one, which is denoted by 3, 2 here. Then we are interested to know the end result, means what is the value at the at 3, 2, at the this vertex. So our algorithm will proceed like that. With 3, 2, it will try to find out the next dependency, as it is dependent with 3, 1 and 2, 2. These curly braces are showing the dependency, and then we calculate one by one. Here actually I have written that consider all nodes allow memory storage. Means here I am not showing that actually in our algorithm we have shown the that if suppose you don't want to store some particular memory, you have that option. So suppose you don't want to store any of the memory, then how if your last node is depending on all the previous values, then how while computing this result, you have to recompute all the values if suppose you don't have the memory to store them. So here as it is mentioned that all nodes are allowed memory storage. So while backtracking, wherever the memory, the required memory comes, we will store that. So here I know that we can see that to calculate this 3, 2, for normal implementation we need 12 steps, and even following our algorithm we need 12 steps. If you want, I can explain in detail, otherwise I will skip that. Now in this example, we are showing that only this column is allowed to store, means only these memories can be stored, other memories are not allowed. So in that case, if I want to know what is the value at this point, then we have to backtrack all the dependencies, and in that case, how many calculations are required? These are actually the algorithm works like it will find all the dependencies, and it will stop when it will get the exact result. So and we have the flexibility that to choose which memory to store and which not, and in that way we can get easily the penalty. Means if suppose if the adversary doesn't want to use all the memories, all the required memories to implement the algorithm, then what is the penalty for that? So here you can see that for this simple example, we need 35 steps. where it was required 12 calculations. Like this, we just we calculated for all the graphs that I have already shown you. We calculated the recomputation penalties, and here this is showing that suppose you need 100% memory, but you have reduced it to 50% or 25% or 12.5%. Then for each graph, how much the penalties are. This through this table we are showing these things. Just if suppose it is written that lambda is equal to 4, it means here this number of rows. Here lambda is equal to 2. So just we are varying the number of rows, and we have shown these results. So by this table, we can have the conclusion. We come to the conclusion that Rig and catenary is exponential in nature, and this is a very simple technique to analyze the time-memory trade-off. And this is from our knowledge, this is the first approach to analyze the time-memory trade-off for the algorithm, which can be implemented which can be represented with a directed assembly graph. So this is a simple technique, and we think we can extend it for many other cryptographic constructions. Till now we have only analyzed with Rig and Catena, and that's all. These are some references.